These are the answers to homework 1C. Question number 1. Kp is 0.225 at 350 degrees Celsius for the reaction 2NO is in equilibrium with N2 plus O2. A tank is initially charged with 0.200 atmospheres NO, 0.100 atmospheres N2, and 0.100 atmospheres O2 at 350 degrees Celsius. A is the forward or reverse reaction spontaneous. This is the reaction given along with its equilibrium constant in terms of the ratio of partial pressures of products to reactants. In this particular case, if you want to calculate which reaction is spontaneous, you'll need to calculate the reaction quotient for the given conditions. The reaction quotient is the partial pressure of N2 multiplied by the partial pressure of O2, which are the products, divided by the partial pressure of NO squared, which is the reactants. If we plug in the individual pressures of each of the different substances into the Q expression, we get a value of 0.250. Because Q is greater than the equilibrium constant and the reaction will eventually reach equilibrium, the Q value will have to change eventually to the equilibrium constant, which means it has to get smaller. So when Q is larger than the equilibrium constant, Q will have to get smaller. And to make Q the fraction a smaller number, the denominator will have to get bigger. And the denominator is where the reactants are. And so therefore you'll have to produce more reactants, so the reverse reaction will be spontaneous. B, calculate the pressure of NO once equilibrium has been established. To calculate an equilibrium concentration or an equilibrium pressure, an ice table will need to be used. So for this reaction, the initial pressures that were given in the problem were 0.200 atmospheres of NO, 0.100 atmospheres of N2, 0.100 atmospheres of O2, and we've already determined from part A that the reverse reaction is spontaneous, which means you're going to create more reactants, so the reactant pressures are going to increase, and the product pressures are going to decrease as the reaction proceeds from right to left. So the change in atmospheres for the NO will be a positive 2x, the change in pressure for the N2 will be a negative x, and the change in pressure for the O2 will also be a negative x. Adding the columns, the equilibrium pressure for NO will be 0.200 plus 2x, the equilibrium pressure for N2 will be 0.100 minus x, and the equilibrium pressure for O2 will be 0.100 minus x as well. These equilibrium pressures are related to the equilibrium constant, so if we write the equilibrium constant expression for this reaction, products over reactants, we know the numerical value of the equilibrium constant is 0.225, and we plug onto the right side of the equation all the equilibrium pressures given in the equilibrium line of our ice table. This can be solved by taking the square root of the entire equation because the right side of the equation is a perfect square on both the numerator and denominator. If we take the square root of both sides of the equation, we get 0.4743 equals 0.100 minus x over 0.200 plus 2x. And then without doing the rest of the algebra, you should be able to take this expression and solve it for x. And x comes out 0.002 with a guard digit of 6. If this is the value of x, now we can calculate the pressure of NO at equilibrium, because in our ice table under nitrogen monoxide at equilibrium, it says its pressure is going to wind up equaling 0.200 plus 2 times whatever x is. If we plug x into the equation, the final equilibrium pressure of NO will be 0.205 atmospheres. Question number 2. For the reaction 2ClF is in equilibrium with Cl2 plus F2, a 2.50 liter flask at 298 Kelvin contains 0.400 moles of ClF, 0.300 moles of Cl2, and 0.100 moles of F2 at equilibrium. A, calculate the numerical value of the Kc for the reaction at 298. So the reaction given is this, and if you want to calculate a Kc, that means the ratio of the molarity of the products to the molarity of the reactants at equilibrium. And so we'll need to calculate what the molarities are for each of the different substances because they've told us how many moles of each substances there are at equilibrium, and we know the volume of the container. So the equilibrium molarity of ClF should have been 0.400 moles over 2.50 liters, which comes out to be 0.160 0.30 molar. For the Cl2, it was 0.300 moles divided by the 2.50 liter container, giving us a molarity of 0.120. And for the fluorine, the 0.100 moles divided by the 2.50 liter container gives us a molarity of fluorine, also to the three significant figures of 0.0, that beginning 0 never counts as a significant figure, 400 molar. So if you know the equilibrium molarities of all the reactants and products, if you write the equilibrium constant expression, we can plug these three values in and calculate what the equilibrium constant is. So the Kc expression will be the molarity of chlorine multiplied by the molarity of fluorine divided by the molarity of chlorine monofluoride squared. And those three values we've just calculated, their equilibrium molarities, 0.120, 0.0400, and 0.160. Squaring the one on the bottom because of the coefficient in the balanced equation makes the molarities cancel out. The equilibrium constant will have no units, but to three significant figures, it comes out 0.188. B, if 0.200 moles of F2 is added to the flask at equilibrium, calculate the new concentration of CLF when equilibrium is reestablished. So the three numbers we have here in problem 2a are the molarities you would have for CLF, Cl2, and F2 if you're at equilibrium. If you change any one of those, the system will not be at equilibrium anymore. So in part B, they've told you you've added 0.200 moles of fluorine. If we divide that by the volume of the container, that means we're really adding 0.0800 molar of fluorine. So this needs to be added to the molarity of the fluorine that was in the container at equilibrium. So the initial molarities now with this added fluorine, because this will not be at equilibrium, it's still 0.160 molar CLF, it's still 0.120 molar Cl2, but adding the 0.0800 molar of fluorine to the original amount makes the molarity of the fluorine 0.1200. Because we've added excess fluorine, that means that that excess fluorine has to react away, and the spontaneous reaction is going to have to be the reverse reaction. If we want to prove that, we can calculate a Q value for these initial conditions, plugging in the two values for the products on the top and the value for the reactant on the bottom, and the Q value comes out 0.563. This Q value is bigger than the equilibrium constant that we calculated in part A, so that means Q has to get smaller in order to reach equilibrium, and in order to get smaller, the denominator has to get bigger, so you have to produce more reactants, so the reverse reaction is spontaneous. If you're producing more reactants, you will increase the amount of CLF, and you'll decrease the amount of both chlorine and fluorine, each by a factor of X multiplied by the coefficient in the balanced equation. Adding the columns will give us the equilibrium molarities of all three substances, 0.160 plus 2X, 0.120 minus X, and 0.1200 minus X. If we write the equilibrium constant expression for this reaction, the equilibrium constant's what we calculated in part A, and we now plug onto the right side of this expression all the equilibrium values found in our ICE table. So the equilibrium constant of 0.1875 with a guard digit will equal 0.120 minus X quantity squared over 0.160 plus 2X quantity squared. If we take the square root of both sides, we get rid of all the powers of X to the second, and we now have an equation that's easily solvable algebraically, and if you can work this out for X, X turns out to be 0.027 with a guard digit 2. The question asked, what is the new equilibrium concentration of CLF? In our ICE table, underneath the CLF, it says its equilibrium concentration is 0.160 plus 2X, so all we have to do is add to that the 2 multiplied by 0.0272 molar, and the final equilibrium concentration of CLF should be 0.214 molar. Question number 3. Nitrogen reacts with oxygen to produce nitrogen monoxide by the reaction N2 plus O2 is in equilibrium with 2NO. The Kc for this reaction at 150 degrees Celsius is 15.0. A flask at 150 degrees Celsius is initially charged with enough nitrogen to make its concentration 0.400 molar. Calculate the concentration of oxygen gas that must initially be in the flask to make the equilibrium concentration of nitrogen monoxide 0.350 molar. So question 3 is an example of a problem where you are not solving for an equilibrium concentration. They're saying what concentration of oxygen must be in the flask initially so that eventually at equilibrium, the nitrogen monoxide concentration becomes 0.350. So we can set up an ice table because this relates equilibrium values with initial values. We know the initial molarity of the nitrogen, but what we don't know is what's going to be the initial molarity of the oxygen. You make that any variable you want. I'm going to choose A. Nothing else was said to be in the container, so therefore the nitrogen monoxide must be 0. If we have both reactants in the container, we know the forward reaction can occur. We don't have any products, the reverse reaction can't occur, so we automatically know the forward reaction is spontaneous, so the reactants will react away, the products will be produced. So we'll lose minus 1x worth of nitrogen, we'll lose 1x worth of oxygen, and we'll produce 2x molar of NO. Adding up the columns, the equilibrium molarities will be 0.400 minus x, A minus x, and then 2x. The equilibrium constant expression for this reaction would be the concentration of NO squared divided by the concentration of N2 multiplied by the concentration of O2. And if we know the equilibrium constant, we can set that constant 15.0 equal to the equilibrium molarities of the products over the reactants. In this case, unfortunately, we have two variables, both the x and the A. The question is asking for A, the initial molarity of O2, so we have to find a way to determine X. And that's determined by the fact that the equilibrium molarity of the nitrogen monoxide is supposed to equal 0.350. And that 0.350, if it equals the equilibrium molarity of nitrogen monoxide, must equal 2x, because 2x is the algebraic equilibrium molarity of NO. So we can solve this for x. X must be 0.175. So in our equilibrium constant expression, we can plug in 0.175 in place of all the x values, and we wind up having an expression now with only one variable, that variable A. And if you can solve this algebraically, you will then calculate what A is, which is the initial molarity of the oxygen, and that comes out 0.211 molar. Question number 4. Complete each of the following ice tables and tell if the X in the ice table will be a large or small number. So in number 4, the first question we have is the reaction between A and B forming C, and the equilibrium constant is 1 times 10 to the minus 9th. You need to recognize that's a very small equilibrium constant. And when you have a very small equilibrium constant, that means when equilibrium is achieved, you're going to have mostly reactants, not very many products. So the information given in 4a is the starting molarities here of A and B and C. Because there's no products, the forward reaction has to be spontaneous. So you're going to react away 1x of A, 2x of B because of the coefficient in the balanced equation, and you'll form 1x of C. The equilibrium molarities will be 1.0 minus x, 1.0 minus 2x, and then x. And the question you're trying to ask is, will x that's in your ice table be a big or small number? So the thing to focus in on is the product. The product is C, and look at the equilibrium line for C. It's going to wind up being x. Now, how do we figure out whether it's big or small? Well, remember, the equilibrium constant is way less than 1. So that means you're going to have mostly reactants at equilibrium. So your two equilibrium values for reactants are going to be big numbers. So the 1.0 minus x is going to be a big number. The 1.0 minus 2x is going to be a big number. But then the products has to be a small number, and look what your product is. It's just x. If that has to be a small number, then that automatically means that x must be small. Let's go to B. B, we're going to do the same reaction, same small equilibrium constant, but this time we're starting with 1.0 molar of C, and there's no A and B. In this case, the reverse reaction has to be spontaneous because you can't have any forward reaction occur. There aren't any reactants present. So you're going to form 1x of A, 2x of B, and you'll react away 1x of C. The equilibrium amounts will be x, 2x, and 1.0 minus x. Once again, because the equilibrium constant is really small, that means you're going to have mostly reactants. So your reactant values, which are x and 2x, are going to have to be big numbers. And the 1.0 minus x, this is going to have to be a small number. So if this is going to be a small number, what does x have to be? X has to be really, really large. It has to be really close to 1.0, like maybe 0.99. So you go 1 minus 0.99, that's how you get a small number. So in this particular case, we would conclude that x would have to be a large number. C. Now we'll deal with a reaction that has a different equilibrium constant. This one has an equilibrium constant of 1 times 10 to the 9th, which you should recognize as a large number. And if you have a large equilibrium constant, that means the numerator in the equilibrium constant's what's big. That's where the products are. So you're going to have a lot of products when you reach equilibrium. If these are the starting molarities, the forward reaction has to be spontaneous. So we're going to react away the reactants. So it's minus 2x of D minus 1x of E. You're going to form 2x of F. Add up the columns. The equilibrium molarities will be 1.0 minus 2x, 1.0 minus x, and this is going to be 2x. Your equilibrium constant now is really, really large because it's way bigger than 1. That means you're going to have mostly products at equilibrium. So what's the products? It's F. What's the equilibrium amount of F? 2x. What does that have to be? That has to be a big number. So that means in this case, because the products have to be a large value, x has to be large as well. Let's go to 4D. Same reaction, but different starting or initial molarities. If we start with 1.0 molar of the product F, that means the reverse reaction has to be spontaneous. We're going to form 2x of D, we're going to form 1x of E, and we'll react away 2x of F. The equilibrium molarities will be 2x, x, and 1.0 minus 2x. Here again, the equilibrium constant's really big. That means you're going to have mostly products at equilibrium. So these products are going to be a big number. So how do you make that a big number? Do you go 1.0 minus a small number, x, or do you go 1.0 minus a big number of x? To make those products small, x has to be a big number so that when you subtract the big number from 1, you wind up getting a small difference. So in this case, x must be a small number. Problem number 5. The equilibrium constant for the reaction 2HCl in equilibrium with H2 plus Cl2 at 25 degrees Celsius is 6.2 times 10 to the minus 54th. A. Why was it unnecessary to be told whether the value for the reaction is a Kp or a Kc? And that's because for this particular reaction, if you calculate delta N, you have 2 moles of products, 2 moles of reactants. When you calculate delta N, it turns out to be 0. So that means the Kp will equal the Kc multiplied by RT to the 0 power, which just means RT to the 0 is 1. So that means the Kp and the Kc are identical. So that means the equilibrium constant of 6.2 times 10 to the minus 54th will equal both the Kc and the Kp. So you could use it for either one. B, without any calculations, what does the numerical value of this equilibrium constant tell you about the decomposition of HCl? It's a really, really small number. That means when you reach equilibrium, you're going to have mostly reactants, not very many products. If you're going to have mostly reactants, that's the 2 HCl's. They're not breaking down very much into hydrogen and chlorine, and so therefore we're going to have mostly reactants at equilibrium. The HCl does not decompose very much is what that means. C. If 0.010 moles of HCl is placed in a 1.0 liter tank and allowed to come to equilibrium at 25 degrees Celsius, will the X in the ice table be large or small? And then what will be the final concentration of the hydrogen gas in moles per liter? So to do this, we're going to set up an ice table for the reaction that we know the equilibrium constant for. And they're telling us here we're starting with 0.010 molar of HCl and nothing else. Forward reaction has to be spontaneous. So we're going to lose 2x molar of HCl. We're going to produce x molar of hydrogen, x molar of chlorine. Adding up the columns, the equilibrium amount of HCl will be 0.010 minus 2x. And the amounts of hydrogen and chlorine will both be x. Because this is a very small equilibrium constant, that means you're going to wind up having mostly reactants at the equilibrium point. So you're going to have a lot of HCl. You're not going to have very many products. So what are your products? Hydrogen and chlorine. What are their equilibrium molarities? X and X. If those have to be small amounts, that means X has to be small. So in this case, X will be a small number, and that's important because when you're doing a numerical calculation, the numerical calculations work out better if you set up the problem so that you know X is going to wind up being a small number. So now we can write the equilibrium constant expression for the reaction, use the equilibrium constant and the equilibrium molarities of the reactants and products. If we take the square root of both sides of this equation, we'll get rid of all x's to the second power, and it'll be an easy equation to calculate. We get 2.49 times 10 to the minus 27th equals x over 0.010 minus 2x. Solving this for x turns out to be the equilibrium concentration of hydrogen, and we get 2.5 times 10 to the minus 29th molar. Part D says if 0.0050 moles of chlorine and 0.0050 moles of hydrogen are placed in a 1 liter tank and allowed to come to equilibrium, will the X in the ice table be large or small? What will be the final concentration of hydrogen gas in moles per liter? So in part D, we'll use the same reaction because we know the equilibrium constant for this particular reaction. In this case, the initial molarities are, there's no HCl present. They're telling you how many moles of hydrogen and chlorine there are, and it's a 1 liter container. So just like in part C, what I've technically done is taken the moles divided by the 1 liter, and that's where I get the molarity, which comes out to be just the same number as the moles, 0.0050, 0.0050. The spontaneous reaction has to be the reverse reaction because there's only products in the container. They have to decompose or react back into the reactants. So we're going to form 2x of HCl. We'll react away 1x of hydrogen, 1x of chlorine, and the equilibrium molarities will be 2x, 0.0050 minus x, and 0.0050 minus x. Now is x going to be a big or small number in this case? Because the equilibrium constant's really, really small, we're going to have mostly reactants in the reaction vessel. There's not going to be very many products. The products have to be small numbers. And what are the products? 0.0050 minus x, 0.0050 minus x. How do we make those small numbers? We need x to be very big compared to 0.0050, maybe 0.0049999. So in this particular calculation, x is going to wind up being a big number, and that's going to cause problems because sometimes we're not going to be able to work out the answer with our calculator. So because x is large, if we try to calculate this now, if we write the Kc expression, plug in the equilibrium constant plus the equilibrium molarities, and then if we take the square root of both sides, we'll now have an expression with only x's to the first power, and we can go ahead and solve this for x. And if you eventually solve this for x, and I move the 2x over to the left side of the equation and multiply the two values on the left side to give us 4.98 times 10 to the minus 27th x. And then if I want to solve this, I would then add 1x to both sides. And if I add 1x to both sides, really I have 1 plus 0.0000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 0.0050. If that's my value for X and I want to know the equilibrium concentration of hydrogen, then the hydrogen's equilibrium concentration will be 0.0050 minus X, which is 0.0050 minus this number we just calculated, 0.0050, and it comes out 0. It didn't work. So this is what happens if you're doing a calculation and you know the X you're using in the calculation is going to be a large number. You're not going to be able to calculate the very, very small answer because you're subtracting two big numbers. And unless your calculator can show values 6, 7, 8, 9 significant figures, you're going to wind up getting a 0 like this. So what we have to do is we have to go back and we have to do what's called a stoichiometric shift. Instead of having the spontaneous reaction, in this case, be the reverse reaction, because when that happens, X is going to be big, we're going to try to shift the products over to the reactant side. So the forward reaction is spontaneous, because in that case, the X value should be small. So what I'm going to do is try to convert as much of the products into reactants as possible. So I'm going to use all of the chlorine because that will react in a 1-to-1 ratio with all of the hydrogen. Turned out to be a perfect ratio. And now 1-to-2 ratio, you're going to form twice the amount of HCl. So if I add these, I'm going to have my new initial molarities, which will be 0.0100 HCl, no hydrogen, no chlorine. So if I use this starting point, this is stoichiometrically equivalent to what I have at the top of the slide, which means I'm going to get the exact same answer for my equilibrium molarities of all three substances. So if I continue the problem, now the spontaneous reaction's to the right, so I'm going to subtract away 2x of HCl. I'm going to add 1x of hydrogen and 1x of chlorine, so my equilibrium molarities will be 0.0100 minus 2x, x, and x. If we think about what x is going to be now that I've done a stoichiometric shift, the equilibrium constant's really small. That means you're going to have a lot of reactants at equilibrium. You won't have very many products. So the products, the hydrogen and the chlorine values have to be small. That means their equilibrium molarities, which are x and x, have to be small numbers. X is going to be a small number. So I can now plug in the equilibrium constant, put in the equilibrium values, and if I solve this, I'm going to wind up getting my value for x, which is 2.49 times 10 to the minus 29th, or rounding it to the correct number of significant figures, 2.5 times 10 to the minus 29th molar.